2015 AP exam question number 1. It says the rate at which rainwater flows into a drain pipe is modeled by the function R, cubic feet per hour, where T is measured in hours over the time interval from T goes from 0 to 8. Since the pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by D of T, cubic feet per hour, for the same time interval T goes from 0 to 8. It says there are 30 cubic feet of water in the pipe at time T equals 0. Now, the first thing when you're doing this is a calculated question. So the first thing you want to do is put these two functions on your calculator, open your window, go to window, open it up from 0 to 8, and then do a zoom fit. So you get a nice picture of what these two functions look like. And also be careful, this is a trig function, so make sure you're in radian mode because radians are in real numbers. Okay, so now let's get it. So that's what I've done. So I want to give you a visual here. So here's what I've done is I put these two functions and I've graphed them. So R of T is the blue curve. That's the amount of rainwater coming into the pipe. Okay, and D of T, which is the red function, is the amount of rainwater being drained out. Now, sometimes when you're doing these kind of word problems, sometimes they get a little confusing. So it's a good idea, if I think of units, then I can help myself get a better understanding of what's going on here. So let's look at area under these curves. What does that mean? Okay, so if I wanted to find the area, any area under these curves, if I just found the area of some rectangle, so I just drew a simple rectangle here. And if I want to find the area of this rectangle, and I'm only interested in units, it would be the area of the rectangle would be base, which is in hours, and the height would be in feet cubed per hour. So the base of the rectangle is hours, the height is in feet cubed per hour. Okay, and if I was to multiply these, the hours go out and I get feet cubed. So the area under these curves is a volume, which is the amount of water. So under the blue curve, which would be the amount of water that flows into the pipe, and under the red curve would be the amount of water that's drained out of the pipe. So that's what that's giving us there. So what I did here is, so now let's write an equation. So I'm writing an equation. This is the total, very simple equation. The amount of water in the pipe at any time T would be the amount of water that was in at the start, the initial condition at time T equals 0, how much water was in the pipe, plus the amount of water that flows into the pipe, minus the amount of water that is drained out of the pipe. So water that's there, water flowing in, subtract water draining out. Okay. So here the area under this curve. So the area under the curve would be a definite integral. That's how you find the area under a curve. That's the definite integral under this function R of T. That would be the amount of water flowing into the pipe. The amount of water that's draining out would be the area under this red region, which would be the definite integral under the function D. And that's the amount of water that's drained out. So here's going on further with this equation here, just to get a look at what's going on. The amount of water total at any time in the pipe would be 30, the initial condition. That's what we started with. That's what we're given at time t equals 30, plus the definite integral of the function R up to any time t, and you subtract the definite integral under the function D. So these are areas under the curves which are volumes of water. So volume of water plus volume of water minus volume of water drained. Now let's look at this a little further here to get a better understanding of what's going on here. If you look at this region here, you see the region here, there's more water being drained out of the pipe than is being added to the pipe. Therefore, the net signed area, the pipe would be going lower because there's more being drained out. So initially, there's 30 cubic feet of water in the pipe. Then it's going to be a little bit's being drained out. And then at this time here, where the two functions are equal, okay, it's going to stop because the amount of water being drained out is the amount of water coming in at the same time, same rates. And then after that, there's going to be more water flowing into the pipe than coming out. And that's what this, and this is a big chunk here. So this is the area, there's a lot more water coming into the pipe now than there is flowing out. So a little bit of water empties out of the tank because the rates here cancel each other down here, but the difference between the two is this region right in here. So there's more water draining out of the pipe than flowing in. Over here, there's more water flowing in than draining out. So let's take a look at this pipe and see if we can see what's going on here. So here's the pipe, and here's the initial water in the pipe. There's 30 cubic feet of water in the pipe at time t equals 0. So now let's see what happens. Let me just hide these guys here. As we move along here, you're going to see that the water is going to drain out slowly because there's more draining up to this time here. So it's going to get a little lower, not much, and then it's going to stop for a second or an instant, and then it's going to start to increase, and it's going to start to increase pretty fast because there's a lot more water flowing in than is being drained out. So let's move it along there. So you see as time goes on, the water is draining out, it stops, and then it starts to flow, but it's going to start to get faster. And then it's going to fill up to a certain point over here. So let's do that one more time. So the water is draining out more so, and then it stops, then it starts to fill up, and then there's going to be more and more going on there. Okay? Okay, let's see if we can answer some of the questions now that we have somewhat of an understanding. It says, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval from 0 to 8? So what I've done here is I've graphed the function. This is the rate flowing into the pipe. This is the region here. So this blue region here, the area of this region here is the volume of water that flows into the pipe over that 8-hour period, which would be the definite integral under this curve. So a good thing to use here, estimating is very powerful because when you do these kind of calculations on a calculator, you can make a simple mistake, get the wrong answer, and not even realize it, okay? So one of the things you should learn to do is really estimate stuff. And so the mean value theorem is very powerful. The mean value theorem says that this region here, I can estimate the area into this region, or this area under this region is equal to the area of some rectangle. And you can see if I was just to draw a rectangle, I could just eye it up here real quickly, and I could say, well, the height of the rectangle over the same base from 0 to 8 would be about 10. That rectangle would have about the same area as under this curve. So this is the accrued estimate of the area under this curve, which is the volume of water, would be about 8 times I said it was about 10, which would be 80. So my answer is going to be about 80. Now, a little more accurate way of doing it, I'm just going to give you a better visual so you have a better understanding here. See, if I was to form some rectangle, and if I was to draw it here, what I'm trying to do is get this area, this region here, to be about the same size as this. Now, you don't have to be very, very accurate. It's just very crude. You just need to estimate it real quick. So what you realize, see, this region over here is under the function, but it's not inside the rectangle. And this region here is under the rectangle, but not under the function. So if I could eye up these two and get them to be about the same size, that means the area under this rectangle would be approximately the same as the area under the curve. So like I said, whatever, it's close to 10 in here someplace. So 8 times 10 is about 80. So I'm going to say the area under this function, or the volume of water that flows into the pipe, is going to be about 80. That's a good estimate. Okay, so now when we do it on our calculator, we're expecting an answer of about 80. And again, you don't make a big deal of it. You just eye it up real quick, 8 to 80. There's your answer. So remember now, so the water here, the amount of water that flows in is the definite integral under this function. So the amount of that flows into the pipe up to time t equals 8 is the definite integral under RT dt. And again, this is volume of water. This is feet cubed per hour. dt is in hours, and you get feet cubed, so the units work out nicely. So you just do this definite integral on the calculator. You should already have this function on the calculator to graph it. And then there's your answer. And whenever you round it to 3 decimal, and make sure you use units when there are units involved in the question. Now let's see what they gave us the points for. They gave us, I took the points. You can look at the solutions later. There's 1 point for the integral, for the definite, or the integrand here, the definite integral of r of t, and 1 point for the actual answer. Part B says, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give the reason for your answer. So what I've done is here, let's look at the graph here and see if we can get an understanding of what's going on. So I took that graph, the function here, and I blew it up a little bit so we could see a little bit better. Here's time t equals 3. And if you notice at time t equals 3 here, the amount of water draining, it's draining at a faster rate than it is coming in, filling. So therefore, if that's true, that means that the amount of water in the pipe should be decreasing because there's more draining out than there is filling in. Okay, so we get a little bit of a feeling from just looking at the graph. So now I'm going to let's do it analytically and see where these equations come from. So this is a good equation to have because I use this quite a bit here. This is the water equation, and this was the water initial condition plus the water flowing in minus the water draining. And here it is in terms of its definite integrals. And so if I want to know, think of a function, if I want to know if a function f is increasing or decreasing, I would find f prime and see if f prime was positive or negative. Okay, so the same thing goes here. That's just a very general equation. So if I want to know if something's increasing or decreasing, I take the derivative of that function and see whether it's positive or negative. So here's my water function. So if I differentiate this function, I'm going to get the derivative of the water prime is going to be derivative of a constant is 0. The derivative of a definite integral, these are like inverses. The derivative of a definite integral, I'm going to get r of t. The derivative of another definite integral, I'm going to get d of t. So the rate of water is going to be equal to r of t minus d of t. And so if you look over here, r of t would just be this point on r of 3. If I want to know it at time t equals 3, r of 3 would be the point on a curve here, and d of 3 would be the point on a curve here. So I just have to go to my calculator and calculate values, find these two values, and subtract them. And that would show, so there's my solution. So if I took these two values right here, and this is the water that's flowing in, and this is the water draining out, you'll see this is greater, therefore it's a negative, because if I take the difference of those two, this is a negative, which is less than 0, and therefore my answer would be the amount of water filling into the tank is less than draining out, therefore the amount of water in the pipe is decreasing at time t equals 3. And here's my answer. Here's what they gave you the points for. They gave you, there's 2 points for this part of the question. 1 point considers r of 3 and d of 3, and 1 point for your answer with the reason. And that's because the reason would be because r of 3 is less than d of 3. Part C says, at what time t on the interval from 0 to 8 is the amount of water in the pipe at a minimum? Justify your answer. And when I say minimum, they mean an absolute minimum. So here, I took the graph from earlier, and here what I'm showing you here are these two regions here, and this red region here means that the red region is the amount of difference between the amount draining and the amount filling in. And that would be, in other words, in this red region here, there's more draining out of the pipe than there's coming in. And this blue region here, there's more filling into the pipe than there is draining out. And that would be the area of this blue region, the amount of water here. So you can see here, it makes sense then if we started with 30 cubic feet in the pipe at time t equals 0, a very small amount drains out because that's the red. There's more red here, so it's draining out. And then it's going to stop. So the pipe is going to be getting lower up to this point because there's more draining than filling. And then there's going to be more filling than there is draining. So now the water in the pipe is going to be increasing. So let's see. So we get a feeling that the minimum would be here at this critical point right here where these two curves intersect. Okay, so now let's try and do this analytically. So how do you do max and mins or absolute max and mins analytically? And the way how do you justify it is you have to compare critical points and endpoints. And that's one of the most common ways of doing it. So an absolute max and min has to be either at a critical point or an endpoint. So here I've listed the endpoints. And it's a good idea to list it this way because it's organized and it makes it very easy to follow what you're doing. So the endpoints, so the water total at time t equals 0 and the water total at time t equals 8, those are our two endpoints. Now the question is, how do we find our critical points? Well, that would be if I want to find critical points like of f, I'd find f prime and set it equal to 0. So if I want to find the critical points of water, I'd find water prime. And if you remember, if we did this in the last part, in part B, and so water prime would be equal to r of t minus d of t, and here I have to set it equal to 0 because that's how you find your critical points. And so therefore R of t was equal to D of t would be the intersection of these two curves. So we just do the intersection of these two curves on our calculator, and that would be the critical point. So these two curves intersect at this point right here, and that we only have one critical point, and that's at t equals 3.272. So now what we have to do is find the amount of water in the pipe at these 3 times. Now we know the water in the pipe at time t equals 0. That was given to us. That's 30 cubic feet of water. And how do we find the water in the pipe at these 2 times? Well, we just use this water equation. This is the amount of water in the pipe at total water in the pipe at any time. And so we have to use this equation, just use it twice, but we just change the time t equals 8. We go up to integral up to 8, up to integral of 8. And at the critical point here, we change t to 3.272 and change it here also. So here are the equations that we have to do, and these are the integrals we just do on our calculator now because we have these functions on our calculator. So we have to integrate the water at total at time t equals 8 would be the 30 plus the definite integral from 0 to 8 of R of t minus the definite integral of d from 0 to 8. And at the critical point, we just have to change the 8 to a 3.272 and do those 2 calculations. So here's our values. Once you do these calculations on your calculator, you get the water in the tank at time t equals 8. I put it up here, and the water at the critical point here was here. And just like we expected, the water started at 30, and then there's it was draining a little bit faster than it was filling in, so it was getting lower and lower and lower up to this point here, and you can see it's lower at the critical point, and then now it's filling in, and it's starting filling in faster and faster, so the water in the pipe is increasing up to this time here. So now to answer your question, you just have to compare these 3 values, whichever is the lowest. We want the minimum, so you answer your question there. So the minimum amount of water in the pipe, the amount of water in the pipe is a minimum at time t equals 3.272 hours. And the justification for that is your table or your comparison between the critical points and endpoints. That is your justification. So let's see what they gave us points for on this question. They gave us 1 point for considering R of t minus d of t equals 0. That would be the critical point. So either one of these 2, they both mean exactly the same thing. 1 point for your answer, stating the time at which you had a minimum. And make sure you say it's the minimum at that time. And then 1 point for your justification, which would be your table comparing critical points and endpoints. The last part of this question says the pipe can hold 50 cubic feet of water before overflowing. It says for t greater than 8, water continues to flow in and out of the pipe at the given rates until the pipe begins to overflow. Write but do not solve. Remember, do not solve it. Just write an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So here's what I did. Here's the equation again for the water in the pipe at any time. And this was the initial condition plus the definite integral of the rate flowing in minus the definite integral of the rate flowing out or draining. I graphed this function over here. So this is W of t. This is the graph of it here. And here's the tank here. So at time t equals 30, at times t equals 30, you can see the height is 30. This is the critical point over here where it got less. And then here at time t equals 8, it went up to 48.54. But you can see the curve keeps going on up. So it's going to begin to overflow shortly after time t equals 8. You can see now it's going to hit 50. The pipe will start to overflow there. So let's look at the visual here too. You can see now I made the height of this pipe 50. So right now it's at 30, so you can see that the pipe starts to decrease up to the critical point, and then it's not quite at the top yet, which is saying it's going to start to overflow shortly after 8 hours. But you didn't have to do that. You just needed to know how to solve this question here. So the only thing we want to know now is the answer would be when is the water in the tank, or excuse me, water in the pipe going to be 50? So the same equation we've been using all along. So we want to know when this is 50, and this is the water initial, and this is the definite integral of the water flowing out, flowing in minus the water draining. and that would be our equation right here. Now let's see what they gave us the points for. They gave us 1 point for the integral. Now you could have put this in one integral, the integral from 0 to t of r of x minus d of x, and then 1 point for the equation, in other words, stating it's equal to 50. Now something you should learn to do is look at the answers the way they give you the answers. So they're out there. So here's the solutions to these questions. Here's the points they gave you. I showed you in each part of the questions. Here's the way they answer the question. So this is the kind of stuff they're looking for. This is what you need, but you got to be very specific, like saying 3 hours and time intervals of when things are happening and so forth. So it's a good idea to look at these. I've pretty much done them the way they have it, but it's a good idea for you to look at them yourself and see what you got the points for.